Hi class, I hope you're doing well. Welcome to the second half of today's lecture. So we're going to continue our discussion of the Fermi Paradox, and in particular we're going to talk about possible resolutions in very broad strokes about ideas people have about what the answer to the paradox may be. There are probably as many resolutions to the Fermi Paradox as there are scientists who have thought about it. You yourself might be able to imagine some resolutions to what it might be. You've certainly been exposed to a lot of the issues and a lot of the things we think about when we think about what the possibilities and challenges and things that may support the existence of life in the universe might be. So, you know, if you have a few idle moments and you want to speculate about this, do spend some time imagining what you think a resolution might be. One of the possible resolutions of the Fermi Paradox, as we will discuss, is an amplification of the rare earth hypothesis. It is possible that our pessimism about the possibility for life in the universe may in fact be the answer to the Fermi Paradox. But I would like to point out that I think as a species, we probably don't subscribe to that kind of pessimism well. And as evidence of that, I will point to our old friend Voyager here. So we discussed Voyager last time when we were talking about looking for extraterrestrial life and starting to think about ways that we might communicate. And we talked about the message in a bottle idea. And Voyager certainly carries on it the golden record. And it is amidships, oh, whoops, my Zoom mirrored reflection here doesn't work so well. I can't even do that when I'm this way. There you go. Here amidships, it's actually bolted on the side of the octagon that you see there. So the thing I like to point out to people is that you don't spend the time that we spent making a record like the Voyager record, putting content on it, trying to imagine every possible thing you can do to help someone decipher it if you are pessimistic about the existence of life elsewhere in the cosmos. And so I will point to the record and the Pioneer plaques as well as evidence that even if we say we're pessimistic about the possibility of life in the universe, deep down in the back of our minds, we do what humans always do, which is we like to subscribe to that hopeful best possible scenario case. Okay, so I will use that as the launching point for today's discussion. So let me go ahead and share a few slides. So there's lots of different possible solutions to the Fermi Paradox. There are lots of scientific papers written about solutions. And in fact, there are lots of books written about this as well, public level books, which some of you may enjoy if you're expanding your reading about extraterrestrial life. So what we'll do is I'm going to start with the Drake equation again, because I think the Drake equation, the reason we introduced it early on is that it's a very good framework for thinking about what parts of the aspects of the possibility of life are we focused on. And many of the resolutions to the Fermi Paradox focus on just one term or one issue that the Drake equation addresses. And so I'll just remind you what it is. We're going to come back and talk about the Drake equation in much more detail next week. But in the context of today's discussion, I just want to remind you what the terms are, because I'll point to a couple of them as we talk about some of these broad solutions to the paradox. I won't discuss every possible solution to the Fermi Paradox there is. We certainly don't have time to do that. Your book talks about much of this in extenso, and so you can certainly read the chapter on this. They will talk about a lot of things. There are some things, I mean, lots of us disagree about what the possibilities are and things that we should or shouldn't think about as resolutions to the Fermi Paradox. Your book, I think, certainly subscribes to some things that I disagree with, and I'm sure some of the things I tell you are things that our authors would disagree with me as well on. But this is the nature of science, right? We're in that state where we're learning, and so we all have ideas, and ideas cannot be refuted or accepted without good data, and we just don't have good data, which will be one of the themes today. Okay, and then we'll end this part of the lecture by just talking about very broadly philosophically, what is it the Fermi Paradox is really trying to tell us? Okay, and we'll use that to launch into next week. We'll start talking about SETI, searching for extraterrestrial intelligence, and we'll also talk about SETI, communication with extraterrestrial intelligence, and that will feed directly from this discussion. So this is the Drake equation as we introduced it way back in the first week of class. We've kind of mentioned it a couple times, but we haven't gone back to it and used it in earnest. You'll recall that it's just these 7 numbers multiplied together, so it's kind of the ultimate astrobiology Fermi problem. The first 3 numbers there we spent a lot of time talking about. They have to do with the nature of planets and the propensity for planets and whether or not they're habitable. And then the last 4 are the 4 that have to do with life itself, if it should appear on a planet. And if you multiply all those 7 numbers together, the outcome is n, the number of civilizations that might exist in the universe, in the galaxy. And there were kind of 2 extremes, you'll recall: the rare Earth hypothesis, which means there are not very many civilizations in the galaxy. There may only be one, us. And the other is the principle of mediocrity, which is the idea that n may be very large. There could be lots of civilizations. And Fermi's paradox, as Fermi expressed it, is starting from the viewpoint that the principle of mediocrity applies. There are lots of civilizations. If there are lots of civilizations, then the paradox is, where are they? Okay, so for this discussion today, for lots of the resolutions that we're going to talk about, we're going to focus on these last 4 terms. There used to be lots of discussion about the first 3 terms, but as we discover more and more exoplanets, I think arguments about the influence that the first 3 terms have on the Fermi paradox are going to become less prominent because we're getting better data. We know what the answers to those 3 numbers are now. Okay, so we're going to focus today, for the most part, on the last numbers here. Okay, so what are the possible resolutions? So the first resolution is simply stated the rare Earth hypothesis, that the presumption that there are lots of civilizations in the Milky Way galaxy is wrong. Okay, the rare Earth hypothesis is that civilizations are few and far between, and in fact, the ultimate rare Earth hypothesis is that we, in fact, are alone, that we are the only civilization in the Milky Way galaxy. This picture is the famous pale blue dot picture. This is the 30th anniversary version of this that NASA released, but this was the picture of Earth taken from Voyager from beyond the orbit of Neptune. So there is no picture quite like this one that demonstrates the notion that Earth is alone. And in fact, the Fermi paradox is easily resolved if we are in fact the only civilization. And so that, in terms of the Drake equation, it really boils down to saying that n equals 1. And so n could be equal to 1. That could be the observation. But the thing that we as astrobiologists would then like to understand is, what is it about the right-hand side of the equation? What is it on the right-hand side that makes n be so small? Does life not form very often? Does intelligent life never form? Are there never communications technologies? What is it about the right-hand side that makes n so small to start with? Okay, so even if this is the resolution, there's still a lot of work for astrobiologists to do, because we still have to know why. Why is this the solution? Okay, now the kind of other idea, which is not really the rare Earth hypothesis, it's actually the principle of mediocrity in action, but the other thing that people often resort to when they imagine a resolution to the Fermi paradox is to say, sure, the galaxy is full of civilizations, but we're the first smart one. We're the first one that has spaceships. We're the first one that has communications technology. We're the first one that imagines we could build robots to spread around the galaxy and explore every planet there is. We're first. Okay, and that very much is the principle of mediocrity. It's assuming that n is greater than 1, although I will point out that if n is equal to 1, if we are alone, then we are also still the first ones, okay? But this argument usually comes from the group of people who believes that we are one of many, okay? And the point there is that they often make is, well, some civilization has to be first, so why couldn't it be us, okay? Well, the Copernican hypothesis really argues against that, okay? And this is the Copernican hypothesis in the broadest sense. The Copernican hypothesis in the broadest sense is there's nothing special about Earth. There's nothing special about the sun. We're one small dwarf star, one small planet in the habitable zone, quite by chance, in some dim, dusty corner of the galaxy. There's nothing special about us. So why should we be first? Okay, if life really is plentiful throughout the galaxy and we aren't alone, then you can assume quite reasonably that life probably formed everywhere in the galaxy at a similar time and at a rate similar to what we've been seeing going on Earth. And so why would it be the case that we are first? Okay, so the way to think about that is to think about a set of worlds distributed through the Milky Way, each of which is perfectly capable of developing a technological civilization that can build the robotic fleet to explore every world in the solar system, or sorry, every world in the galaxy. Okay, now they won't all do it at the same time. Maybe they're within 1,000 years of each other. Maybe they're within 100,000 years of each other. Maybe they went through an extra extinction. Maybe one of them went through one fewer extinctions than we did on Earth. Who knows? But the point is we're scattered. We're all very far away. But life formed very soon after the planets developed in their respective solar systems. And so we all began developing very early on in the history of the galaxy. Okay? So in this idea then, what the Copernican hypothesis tells us is that there is no first. There's only together. We all kind of form the same way and at the same time and with the same schedule, because there's nothing special about us, or we're alone. Okay, in which case we are special. Okay, so if we all develop at roughly the same time, then we would expect, given the vast distances involved, that we would start spreading throughout the galaxy at roughly the same time. So if you imagine Earth is there at the orange dot, okay, and we start spreading out, it's going to take Voyager 40,000 years to get to the closest star. Okay, and if the blue dot starts 10,000 years after us, that's not going to make very much difference in terms of how long or how far it takes our spacecraft to get from Earth. And so if you imagine all of these worlds expanding outward, the truth is we're all going to cover the galaxy at roughly the same moment in time in roughly the same way. Okay, and so the fact is we can't be first, because if every world's evolving, then the chances that we're first is extraordinarily small. And even if we were first, in very short order, we would expect evidence from another civilization to reach us very quickly. Okay, so this is the argument against the we are alone. This is the other extreme, the principle of mediocrity. We're not first, we're just one of many. And if we're one of many, then all of us are trying to do this. Okay? Now, there are many assumptions that are made in that argument, namely that we want to explore the galaxy, and if we want to explore the galaxy, of course, every other civilization wants to explore the galaxy, okay? Well, many of the other resolutions to the Fermi Paradox kind of focus on those points, okay? So imagine a civilization is quite happy to live on their home world and not go gallivanting among the stars looking for other life, okay? There may be no strong desire on a part of a civilization to expand beyond their home planet. And indeed, if you look at the history of life on Earth, we don't know of any other technological intelligent species that existed on Earth until our time. Life has been on the planet for lots and lots of years. The dinosaurs, they never built space stations, as far as we know. They didn't think about going to the stars, whatever. So it may very well be the case that there are civilizations that have intelligent species. Maybe they have technology, but they just don't have any strong desire to leave their own world. Okay. Now, the ultimate argument against that is that someday they have to leave their worlds, because every star in the galaxy is going to die someday. And so if the species wants to survive, then it will be imperative that they leave their world, because ultimately the star will die and the world thus will die as well. Okay, so there's no real term for this in the Drake equation. Okay, but the notion that you don't want to expand out could be refined in the Drake equation by looking at FC. FC is the fraction of worlds that develop communicative technology, or the fraction of worlds that develop technology that they use to communicate out beyond their own sphere of influence, okay? So that's the one place where this could be used, and one of the things that we talked about early on is that you could take any one of those terms in the Drake equation and tease it out into much finer detail. And so this is an example of one of those finer details that you can tease out, okay? Now, in another example of a sociological concern, of a sociological fact about a civilization, is they may just decide that they don't want to interact with others, not because they're happy, but because they're scared of other people, like my cat here hiding in the sink at the vet, or maybe they have some directive to not interfere with other civilizations. Okay, so this is a famous tenet in science fiction. Those of you who are Trekkers will recognize this as the prime directive from Star Trek, which of course they say but almost never pay attention to. Okay, but these are both very obvious resolutions to the Fermi paradox. Maybe there are civilizations all over the galaxy, but they're either scared of meeting other civilizations. We certainly see plenty of xenophobia in our own civilization when we think about other cultures, particularly here in the United States. And we also have this notion that we sometimes shouldn't interfere with other progressions in other civilizations' activities, okay? And those very well could be aspects of an alien civilization as well. Again, there's no term for this in the Drake equation, but you could imagine in that communications fraction, we've bound up in there the idea in that number that a civilization wants to communicate. So if you tease out and break it down, you can include these kinds of ideas. Now, another possibility is simply that civilizations don't live long enough to make the effort to spread through the galaxy. Okay, certainly the dinosaurs were wiped off the face of the planet before they got smart enough to build rockets. Okay, maybe they would have never built rockets, maybe they would have, who knows, okay? So natural catastrophes are certainly what killed the dinosaurs. Maybe they happened before a species develops technology, but maybe it is very common for civilizations to destroy themselves through things that we see going on in our own civilization, things like climate change, things like war. These are all things that can cause a society and a civilization to collapse. This is actually an area of academic study. Those of you who are in sociology may know this. Societal collapse is a theoretical area of study. And indeed, we have historical examples, and we'll talk about some of those next week. But it may be the case that it is common for civilizations to collapse before they can extend themselves into that exploring the whole galaxy mode. Now, in this case, we're really talking about L, that last number in the Drake equation. And next week, when we talk about this again, what we will discuss is the fact that this really does seem to be the one number that has the most influence on the Drake equation, because this number can range everywhere from maybe 100 years to hundreds of millions of years. And so it provides a vast range in possible outcomes for the total number of civilizations in the galaxy. Okay? Now, this one, this is actually one of the ones that I think about a lot. And when I imagine resolutions to the Drake equation, I think about this one the most, probably because I have a lot of interest in climate and our current impact that we have on the biosphere. And so it naturally drives those kinds of thoughts and discussions about the lifetime of our civilization. But in this in particular, I will point you to what I think is one of the greatest explanations about the resolution of the Fermi paradox there is, and it really is focused on this number L. So it's actually a song by a guy named Peter Mulvey. Peter is a folk artist here in Wisconsin, so he's very near to our area. So sometimes he travels through the area and you'll have a chance to go see him, particularly in the post-pandemic world. You can certainly watch him. He's doing live online streaming concerts now. He's really great. I enjoy his music a lot. But he had a really great album many years ago called Letters from a Flying Machine. And on that album, he has a song about a friend of his named Vlad, who's an astrophysicist. And he recounts in the song a discussion he and Vlad had about exactly this topic, about the Fermi paradox, about where are all of the aliens in the universe and why haven't we met any of them. Okay, it really is a very fantastic and lucid explanation. The song is on YouTube. There's a link to one of them there. He also did it at a TEDx, so you can find it at his TEDx performance. And then a few years ago, he had a Kickstarter where he produced a book where he took the lyrics of the song and some really absolutely fantastic illustrations by an artist named Peter Nevins. And so if you go to Peter's site, you can get a copy of this book. But it really is, to my mind, one of the most excellent and extraordinary explanations for the Fermi Paradox. Very clear and very lucid. And so please do take the opportunity to go watch it. It is a great rendition and a great discussion. Okay? Okay, so in the end, this is what we really care about. What is the Fermi Paradox really trying to tell us? I think the first thing it's really telling us is we really don't know enough about the galaxy yet, right? We're doing our best to try and put values on the numbers in the Drake equation so that we can estimate the number of civilizations in the galaxy. But we are getting better at some of the numbers. We're certainly just discovering plenty of exoplanets and so on. But we still don't know enough about life and the propensity for life and what the conditions are on those exoplanets we're discovering. And so it's really still our understanding of what those last four numbers are, particularly here in the galaxy, that is limiting our understanding. You could argue that it's really that we don't know enough about life yet. Certainly that is true. Even here on Earth, we are discovering lots of limitations to our understanding of life, particularly when we look at the number of different extreme environments in which we find life. We're discovering it all over the place and able to adapt and overcome in rather extraordinary ways. But that limiting knowledge about what life is all about is part of our not understanding the nature of life in the galaxy as well. And in the end, this has been our story the whole semester. What we need is we just need more data and we need better data, right? This is a question that can certainly be answered. And it's a question maybe not answered definitively, but it's a question where our knowledge can increase far beyond what it currently is by simply learning more. And if our data gets better, our understanding of these questions will get better, and we'll have a more satisfactory answer to the Fermi Paradox. Are we alone or not? But I think the most important thing about the Fermi Paradox is that it's probably telling us something about our own future. If life is plentiful and we haven't encountered life yet, then it's telling us something about our future when we are at a stage where we could fill the galaxy and possibly meet other life. If life is not plentiful, if we are one of the few, if not the only, then that's also telling us something about ourselves. And all of those lessons to be learned, I think, are rather extraordinary and rather important. They're very deep. They have deep implications and deep philosophical implications for the way we conduct ourselves and what our future as a species would be. And, you know, there are lots of eloquent writings and eloquent speculations about that. But most of you know by this point, I'm a big fan of Carl Sagan. I do what I do because I was exposed to Sagan at just the right point in time. But I think he very succinctly summed this idea up here in his book, Pale Blue Dot, which is about the uniqueness, the smallness of the Earth. And in there he wrote, "It's been said that astronomy is a humbling and character-building experience. There's no better demonstration of the folly of human conceits than what you can learn through the study of astronomy." Humans regard themselves often and widely as being the apex species, the ultimate authority on many things in the cosmos. And it certainly is true that when you expose yourself to the bigger picture, to the universe at large, you really do have to come to grips with all of those conceits that we as a species have. Okay, so that's all I'm going to say today. I will leave you here. So I do have a copy of Peter's book, Vlad the Astrophysicist. I just wanted to show you some of the art and pictures inside. It's just beautifully and lavishly illustrated. It has the lyrics of the song in there, and Peter Nevins just did a fantastic job in his illustrations. And it is very much a thought-provoking and just really beautiful book. the song itself is one of my favorites of all time. And so I certainly do encourage you to spend some time going and looking for Vlad the Astrophysicist. Okay, so that's all I'm going to say today. That's it for the week. Next week is our last week of class, and we will talk about the search for extraterrestrial intelligence. So have a great weekend. Do take care of yourselves and be safe out there. I'll talk to you soon. Bye-bye.